Gentlemen, my name is Karim Sharman. For the next 15 minutes, I will talk about the application of unsupervised machine learning to assist seismic interpretations. Basically, I divide my presentation into 5 parts, started by introductions, motivation and objective, and dataset. Next, methodology and workflow concept, and next to resolution a result of PCA and self-organizations map, and then evaluations, and finally we concluded our work. Let's start by the first point, motivation and objectives. The problem of limitation of conventional seismic interpretations to image subsurface and tiny reservoir and extract interesting lithology by using conventional method of seismic amplitude, and also the time consuming by interpret for high volumes. For example, this carry out faulty mapping of this horizon in this inline section extracted from the 3D volumes of this project, where the interpret want to map this horizon at depth of 2.7, which is called huge informations. We can see here when it zooms, when it's highlighted the anomaly, there is some downs in the left side, which is have a different story. We can conclude here that these interpretations in the left side, it might be in taking different interpretations. These bring our proposed method using unsupervised machine learning and multiple attributes to enhance seismic interpretations with the key vendors of improving lateral resolutions and vertical resolutions of seismic using self-organizations map with optimum attributes. For the next slide, we'll talk about the dataset. The dataset is a Volve dataset field. This dataset is in the Norwegian's North Sea, located about 200 kilometers from Stavanger. It is Equinor dataset, it's open dataset, which is it's offshore dataset, which is collected by using two vessels you can see here. So one used by source and the other one is collecting the data by using cables, and all the hydrophone is in the seabed. This method is called OBC, which is Ocean's Bottom Cable. This data is acquired by a company they called RTX, which is a reservoir exploration technology, and is processed by Schlumberger in 2010. The main reservoir in this area, which is here, you can see it is the greens, it is the Volve field, which is oil Jurassic sandstones. And you can see here in this map, which is highlighted by the orange colors, which is huge formations where there is different faults here, and this is the directions of the wells drilled here. This brings us our methodology workflow to solve these problems by reading the data and make some analysis on this data and highlight the interesting area of study, and after that calculated multiple attributes, the most attribute that used for interpretations like geometry, instantaneous and amplitude, and after that we feed this attribute to the PCA, which is taking the most variance attribute and how the attribute is contributing in these PCAs. The output of these PCAs is optimal attribute that can feed the neural network self-organization map, and after that we have some evaluations. This workflow is work in different space, started by survey space, which is the original space of the data. After that, when we're moving to attribute and we concatenate all attribute in one volumes, we have attribute space. After that, we feed this attribute to the sum, which is neural network. We move to a neural space. In these pictures, we can summarize the concept very quick, which is we have seismic amplitude, calculate the attribute for different volumes, and we have concatenate sorted all these volumes in one volumes, and we have a high variable data set of attributes. We feed this attribute to the PCAs to have the various attributes, the most variance attributes, and also reduction of the variable of the volumes. Feed this one to the sums, and we get finally new volumes with color map. Seismic data. Seismic data used here is 3D volumes, ball volumes, which is they have three coordinates, which is L line, which is the direction of the vessels of the cables, and also the cross line, which is the cross of the cables, and we have time slice, which is a depth, which is in two-way times. The area of interesting here is between 2000 millisecond and 29 millisecond. This brings us to seismic attribute that we used here in this project. We use 10 different attributes summarized in this table here, and their category and their use. We just highlighted some attributes here. For example, the instantaneous envelope, which is calculated, this you can see it here, which is calculated by the Hilbert transformations. We can see here this is seismic amplitude, which is the original ones, and this is the envelope attribute calculated when you can highlight it here as a very contrast impedance of some lithology or and direct hydrocarbon indicators. The second attribute I want to talk about it, which is instantaneous phase. This is very important, which highlight they are used for lithology and stratigraphy. You can see here that highlighted very well resolutions, vertical resolutions, and also we can see here in this area maybe there is some discontinuity. The third such attribute I want to highlight is the sweetness, which is calculated by the using the envelope attribute and divided by the dominant frequency. This attribute is mainly used for lithology and also for porosity and stratigraphy variations. We can see here this dominant in the colors and reservoirs and also some pore hairs. To evaluate this attribute, we do a simple correlations matrix, and we remove the lowest. We take the lowest attribute correlated with others to remove the redundancy of the attribute before we feeding this attribute to the sums. For example, we see here that RMS and sweetness and trans, they have high correlations between them, and we take the lowest ones, we take the RMS amplitude as the input for PCA as attribute. Same also for instantaneous phase and instantaneous band width, which is high correlations. We eliminate one and we take ones. The second slide, this slide presents the result of the PCA. The PCA is highlighted the most variance attribute component, which is situated in component 1, 2, and 3. We limited our resolutions to where there is even vectors greater than 90%. To evaluate this, the attribute after the PCAs, we have correlations matrix. Also, we see that some attribute they correlated very well in PCAs instead of and the others they correlated with low values. For example, we see PCAs, the attributes instantaneous bandwidth, they have high values, which is correlated very well with PCAs. And also we can see here in PCA3 the attribute quadratic amplitude, they have a very high correlations in the PCAs. But in general, we cannot see other, for example, another attribute which is highlighted here in PCAs have the same values in other PCA principal components. Also, we check the evaluations by using also the correlation matrix between the PCAs. We can see all the values here in the PCAs is very low, which show that there is no redundancy of attributes inside the PCA and between the PCAs. The output of the PCAs is summarized here. This is the attribute where for the PCA1s, and this is PCA attributes for PCA2, and this is PCA classification for PCA4, and this is for PCA3. Each attribute, each classifications, and each group of attributes highlighted some geological features. We can see here for PCA they highlighted the centers of the structural geologicals and some portions of reservoirs. If you see here for PCA, they highlighted the edge of the anticlinals or geology features. If you can see here also for PCA3, same also they have some features they highlighted. In general, the PCA is most variance is located the most variance attribute, the optimum attribute that we can feed for feed a sum. Also, the contribution of the attribute in each PCA. Using this attribute and feeding the sum, which is the self-organization math and neural network, this is our input here, which is a seismic reflection amplitude. We can see and we use a different topology neural network. It means clustering nodes. For example, this one we use 4x4 nodes, 8x8 and 12x12 and 16x16. This with color code. This bring all more resolutions to our data. This is analyzing in time slice. The second analysis is in inlines. We can see here also there is some tiny reservoirs and some different hydrology, and where the stratigraphy is very well comparing to the original data, and we can interpret more. To evaluate our method, we use three algorithms: silhouette coefficients and Klansky, Harbs, Andes, and Davis, Bolden's, Andes. And for the silhouette and Klansky, Harbs, we take the highest values, and for Davis, Bolden's, we take the lowest values. And if you see the three algorithms, they highlighted that the clustering number ones, which is 4x4s, is the optimum solutions for our data. For optimal solution for our data, this is bring our resolutions, and you can see here in this slide that this is our input. You can see here this is our target objective, which is anticlinals feature geologicals, and you can see here there is our target with more black colors. This is reflected the fault, and this is the dome of the reservoirs, and also there is the highlighted some separate colors here for reservoir, and you can see it here in vertical analysis, which is inlines. You can see here there is the red ones, it is some new reservoirs. Also, the problems of the mapping the horizon, it's very clear that it is not going up to downs, but they have solutions to get it in right positions, comparing to the first ones, which is going down like here. Another comparisons, which is for the attribute, we are using PCAs for our optimum solutions. The second comparison we use human selections. You can see that the resolutions is different, where the PCA give more resolutions than the human selections. This concluded our work that the application of supervised machine learning and attribute bring more features and geological features to our data. The positive point that seismic attributes improve laterals and vertical resolutions comparing with amplitude data, and also the PCA provide insightful information regarding to attribute not being considered by interpret. We use the comparison between BCA and humans. For the sums, also the classification, they highlighted some thin reservoirs, or also extracted some lithology and have clear stratigraphy for interpretations. And also the algorithm is very easy to use and it's simple, and we can use it to reduce time consuming for interpretation of high data. Of course, there is some limitations, which is summarized here in 3 points, that the attribute analysis has limitations in time consuming because the attribute volumes with multiple attributes is hard to analyze. Also, the attribute selections require a human experience, and the application also of the application on area with the knowledge of geology and geophysics. This brings us to future work that we need to tie together seismic data with well data. The well data, we recommended that we have two types of data, which is log data for petrophysics analysis and the core data for rock physics analysis. We apply the same sum algorithms, and another steps you need to include it is the automatic selection of attributes, avoiding the human selections like using deep learning. This is I concluded my presentations. Thank you for your attention, and this is our reference, and thank you.